Welcome. Now we discuss on third unit, which is solution properties. I am Dr. Ravi, working as assistant professor in the Department of Pharmaceutical Engineering, BVRIT in Sapur. So the third unit objective is understand to determine the thermodynamic liquid properties. So outcome of this unit is student after the completion of this unit, student able to understand how to determine the thermodynamic solution properties. So this is a mapping of third unit outcome with respect to the engineering program outcomes. In the past two units, we have seen that how the first unit outcome and second unit outcomes are helping to the engineering program outcomes. In the same way, third unit also the outcome is helpful to give the engineering knowledge to, and also it gives the solve the complex related problems. And next the engineering and society related problems, how to solve it, how to handle that, like so we have already seen that. So last one, PO12, is for lifelong learning. So whatever the outcome you learn from that this unit, this will helpful to you for your lifelong learning. Next one, the unit 3 content. The first one, in this unit, these are the content we are going to discuss. First one is the partial molar properties. Second one is the chemical potential. Third one is the concept of fugacity and activity and their calculations. Fourth one, ideal and non-ideal solutions. Fifth one, Gibbs-Duham's equation. Sixth one, property change of mixing. And finally, this unit will be completed with excess properties. First, we'll see the partial molar property. Before going to discuss about the partial molar property, first we see a little introduction about this unit. Generally, in the last two units, in the first unit we discussed the fundamental thermodynamic properties. In the last unit, the second unit, we discussed the single compound or mixture, fluid mixture, how to determine their thermodynamic properties using the correlations. So now in this unit, we discuss how to determine the solution thermodynamic properties. Here the solution means the homogeneous, it is a solution means here is a homogeneous mixture of two or more compounds in gas or liquid states. So whatever the correlation we have for pure and mixture fluids, here we cannot use them for the solution properties because here the solution thermodynamic properties are different. So first, next one is the partial molar property. Generally, when the compound is in a pure state, pure means a single state, whatever the property it has, so that is different. When it is in a solution, the properties that is different. Meaning is, for example, any compound in a single state, it is having the one mole volume, one mole quantity is occupied when it is in a pure state. But the same one mole of that compound, when we add that compound into the solution, the the volume occupied by the compound are is different, the properties of that compound are different. Means, so when it is in a single state, it is, and when it is in a mixture, when the compound is a mixture, this pure compound loses its identity when it is in the solution. So that's the reason. So if you want to if you want to determine the what is the compound property when it is in a solution, so so that can be determined from the partial molar property. So here it is the partial molar property is represented with m bar. In that solution, for any compound, if you want to determine any compound molar property, so that is represented as m bar I, that is equal to dou by dou nm by dou ni. Means with respect to the change in moles to that particular compound, and how the total molar property is changing at a constant temperature, at T means constant temperature, constant pressure, N J not equal to I means except the compound which you are interested. Apart from that, all other compound moles are kept constant. That is N J not equal to I. Here M represents M bar I represents the partial molar property of the compound I in the solution. So M represents the molar property of the solution. Means per unit mole, what is the solution molar property? Ni represents the number of moles of the compound. Here N represents the summation of Ni, means summation of N1 plus N2 plus N3 plus so on. So MT represents the M represents the for single mole what is the solution property, and MT represents the what are the total moles are there in that solution compounds in that whatever the total moles of that compounds, that moles into the molar property, means that is the MT is the total molar property of that solution. So T is the temperature, P is the pressure. I already said N J not equal to I means the apart only I is number of moles of all components in the solution, other than the number of moles of I are kept constant. Means other than the I remaining all kept constant. So what is the physical meaning of this partial molar property? So for example, you take a huge volume of water. In that you add 1 ml of water. So the 1 ml of water, what it is having, it is the volume occupied by the 1 ml of water when it is in a pure state. And when that 1 ml is added to the huge volume of water, then the volume is increases by 18 into 10 power minus 6 meter. The same 1 ml of water, when it is added to the huge volume of ethanol, then the volume increases by 14 into 10 power minus 6 meter cube. The same 1 ml of water, when it is added to huge volume of water, the volume change, the volume occupied by that 1 mole of water is different in the water, and the volume occupied by that 1 mole of water in the ethanol is different. So what is the meaning of that? The partial molar property means in the solution, the pure compound, it loses its properties. Okay, then what is the property, or what is the property it is having in its solution? So that is a partial molar property. These partial molar properties can be determined by various methods. Here we'll see three methods. First one is the analytical method, second one is the graphical method, third one is the tangent intercept method. First one is the analytical method. Analytical method using the formula, that is m bar I is equal to dou mt by dou ni at constant temperature, pressure, n, j not equal to I. So using this analytical formula, we can determine the partial molar property of the particular compound in the solution. Next one is the graphical method. So in the graphical method, so molar property, molar total molar property of solution. So graphical method. So in the graphical method, for example, if you want to determine any particular compound, that I compound, if you want to determine the what is the partial molar property, then draw the graph between the with changing the number of moles of respect to that compound with respect to the change in the total molar property. With the number of moles of that compound, if it is changing, then how the total molar property of that solution is changing. In between that, when you draw the graph, so after that, draw a tangent at one particular point. Okay, so draw a tangent at a particular point. The slope of that tangent is then, of course, slope of dou m. We know that dou change delta y by delta x, that is dou mt by dou na. Okay, at a constant temperature means from the graph we can determine the partial molar property of the particular compound at constant temperature, pressure. Other compounds moles are kept constant. So that way we can determine the particular compound's partial molar property. Next one is the tangent intercept method. This tangent intercept method is widely used method for binary solutions. So here, for example, the total molar property consider the m. The molar property you consider the m, and in the binary solution you take any compound, like let's say x1. X means let's say first compound mole fractions, and draw the graph between the molar property and the mole fraction of that particular compound, and draw the graph between that. In that, at what mole fraction you want to determine the partial molar property of that compound, then at that point, at that mole fraction, just draw a tangent and extend the tangent to, let's say, A to B. So then this tangent will intersect at the y-axis at A, and another right hand side it will intersect y-axis at B. So at here at x is equal to x1 is equal to 0. X1 is equal to 0 means, what is the meaning of that? The mole fraction of x2 is equal to 1. At x2 is equal to 1, so this is the partial molar property of the second compound. So this is at 1, x1 is equal to 1 means x2 is equal to 0. X1 is equal to 1. The partial molar property of the first compound is equal to dB, the distance between the D and B. The partial molar property of the second compound, and that is x2, here is and the distance between the A and C. Okay, so and at whatever the wherever mole fractions you want to determine. For example, here we want to determine that is at this mole fraction, the slope is equal to, we can determine the what is the at that mole fraction, what is the partial molar product of that compound. So that way we can determine. So by using these three methods, was analytical method using the analytical formula and a graphical method, we can determine the also we can determine the partial molar property. And next one is the tangent intercept method. Also, the advantage of this method is by using the same graph, we can determine the in a binary solution for binary solution, the same graph we can determine the partial molar property of the two compounds from the same graph. That is the advantage of tangent intercept method. Next one is the determination of solution total molar property. So now up to now we have seen in a solution various compounds are there. How to determine the compound partial molar property in the solution. Now how to determine the total molar property of the solution. So for that, consider, for example, the total molar property of the MT is a function of temperature and pressure and amounts of the compounds in that solution. So that is N1 comma, that is MT is equal to F of T temperature comma pressure comma N1 comma N2 comma N3 and so on. Okay, so N1, N2, N3, so on are the number of moles of the 1, 2, 3, so on respectively. So now, for a little change in the temperature or pressure or number of various moles of components, then we can write in a complete derivation, that is dmt, applying the derivation, dmt is equal to dou mt by dou p, and with respect to the because we are saying with the changing the small change in the temperature, pressure or moles of all the compounds, how the total molar property changing. That's the reason dmt is equal to only with the partial derivative, means only with respect to the pressure at constant temperature and constant moles, how the total molar property change. That is dou mt by dou p at constant temperature and constant moles at dp into dp plus dou mt by dou t with respect to the only temperature at constant pressure and number of moles, constant number of moles dt plus, so next one, number of compounds. So for example, first compound dou mt by dou n1 constant temperature, pressure. So other compounds moles are we kept constant, n2, n3, so on, dn1 plus dou mt by dou n2 constant temperature, pressure, n1 comma n3 comma n4, so on, into dn2 plus dou mt by dou n3 at constant temperature, pressure, n1 comma n2 comma n4, so on. So like so on, we can write in this way, dou mt by dou ni constant temperature, pressure, n j not equal to I dni, like that. Okay. For example, this is the expression for what is the change in very little change in total molar property with respect to the changing of temperature, pressure, number of moles of the compounds. So, for example, now we consider at constant temperature, so that is dt is equal to 0, constant pressure dp is equal to 0. So now then this expression converted into dou mt is equal to so these first two, because at constant pressure this is equal to 0, this is equal to 0, and constant temperature this is equal to 0. So remaining terms will get that dou mt is equal to dmt is equal to dou mt by dou n1 at constant temperature, pressure, n2 comma n3 comma n4, so on. So the remaining expression we will get. So this remaining expression we can write because summation of I is equal to 1 to n 1 to n dou mt by dou ni constant temperature pressure n j not equal to I into dna. That way we can write. Okay, but we already know that m bar I is equal to dou mt by dou ni constant temperature pressure n j not equal to I. We already know. So that we can write this one dou mt is equal to because from here this is equal to this full thing is equal to m bar I. So that's we can write this dou dmt is equal to summation I is equal to 1 to n m bar I into dni. Okay, so this one we can write as if you expand this d m t is equal to summation means m1 m1 bar dn1 plus m2 bar dn2 plus m3 bar dn3 plus so on, like we can write. Okay, so integrate this expression both sides, then we'll get the integration of d mt is equal to m1 integration of bracket start m1 bar dn1 plus m2 bar dn2 plus m3 bar dn3 so on. Okay, so now we can write this one integration of d m p is equal to integration of d m t is equal to, we can write this integration for individually, like integration of m1 bar dn1 plus integration of m2 bar dn2 plus integration of m3 bar dn3 so on. So when you integrate that, we'll get the, what do you get? We get mt is equal to m1 bar n1 plus m2 bar n2 plus m3 bar n3 so on, like we get. Okay, now apply the n is the total number of moles, the n capital N. Apply both and divide with multiply and divide with the n for right hand side. Then so after getting that, we can get that after that mt is equal to m1 bar n1 plus m2 bar n2 bar n2 plus m3 bar n3 so on, multiply and divide with the capital N means total number of moles. So this is m2 is equal to, now m1 bar multiply with every term n1 by capital N plus m2 bar m2 by capital N m3 bar n3 by capital N 1 by n. Okay, this n1 by small n1 by capital N we can write in a mole fractions. Okay, means mt is equal to m1 bar x1 mole fractions m2 bar x2 plus m3 bar x3 so on, plus so on by 1 by n. So for this when you consider this So consider for n is equal to 1 mole because total number of moles are the consider 1 for example. Then we will get the expression, final expression is m mt is equal to m1 bar x1 plus m2 bar x2 plus m3 bar x3 so on. So in this way we will get the um, uh, total molar property of the solution in terms of the moles or in terms of mole fraction. That is that mt is equal to m1 bar. Total molar property of the solution is equal to partial molar property of the first compound into number of moles plus partial molar property of the second compound into second compound number of moles plus third partial molar property of the third compound into number of moles of third compound so on. So you can write that we can write it in terms of summation ni summation uh, summation ni mi bar. Okay, so in the mole fraction also we can write mt is equal to m1 bar partial molar property, total molar property of the solution is equal to partial molar property of the first compound into first compound mole fraction plus second compound partial molar property of the second compound into second compound mole fraction so on like that. So we can write this is in two ways like m of t is equal to summation ni mi bar or m of t total molar property of the solution we can write summation xi into mi bar. So that we can write. Now we have seen first in the first how to determine the means what is the partial molar property. So the expression we have seen. Later, what is the meaning of the partial molar property? After that, we have seen how to determine the partial molar property of the compound in the solution. So three methods are there: analytical method, graphical method, tangent intersect method. So now after that, we have seen how to determine the total molar property of the solution. So the total molar property of the solution is equal to summation of ni into mi bar or summation of xi into mi bar. That is the total molar property of the solution. So these are the some problems are there, so that we can do later. Next one is the chemical potential. So before going to discuss the chemical potential, first if two systems are there in a thermal equilibrium, for example the two systems are there in a thermal equilibrium. So what is the index means if the two systems are having the same temperature, then we can say that these two systems are in a thermal equilibrium. In the same way, if the two mechanical systems are in a mechanical equilibrium, so when the two mechanical systems are having the same pressure between them, then these two systems can have a mechanical equilibrium. They are in a mechanical equilibrium. In the same way, the chemical potential is the index for the chemical equilibrium. If the for example reactants are there, products are there, the reactions are converting into the products. Whenever the reactants chemical potential and product chemical potential are equal, then we can say that from that we can say these reactants and products are in a chemical equilibrium. So the definition for the chemical equilibrium is it is a energy that can be absorbed. This chemical potential is a energy that can be absorbed or released by adding or releasing the particles to the system. When a system is there, in that system, when the number of particles are adding, for example, reactant products are there. the reactants are converted into the products. The particles are added to the products. So the chemical potential of the products are changing. But the reactants, the chemical potential, the reactants, the reactions, because of the conversion, the particles are decreasing. I mean, so then the chemical potential of these is also changing. So whenever the 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 total energy, that is chemical potential, the total energy is constant between the two systems, then we can say that they are in a chemical equilibrium. So the chemical potential is the energy that can be absorbed or released due to the change in the particle number. If the particle number is not changing, then there is no means that the reactants are not converting to the products. Means there is no number of particles adding to the products. Meaning that there is no change in the number of particles, so that the chemical potential of the reactants remains constant. It is in the same way the reactants are not conversion is happening. Then what is happening? Then there is no removing of particles. Then the chemical potential is not changing. So like that. So there are both are in a chemical way. The chemical potential of the any compound in a solution is equal to the partial molar free energy or partial free energy. Okay, so that can be represented as chemical potential is represented as mu I. Mu is equal to G I bar. Okay, so we already know that the Mi, partial molar property of the compound in a solution, is equal to dou Mt by dou Ni at a constant temperature, pressure, Nj not equal to I. So from that we can write this chemical potential of any particular chemical potential of the compound in a solution is equal to that compound partial gives free energy. Okay, so this we can write G I bar is equal to dou G total by dou Ni at a constant temperature, pressure, Nj not equal to I. So now from this we can write, because we can write chemical potential is equal to dou Nt by dou Gt by dou Ni, constant temperature, pressure, and J not equal to I. So here the Gt is the total free energy of the solution. So the total gift free energy of the solution is a function of temperature, pressure, and number of moles of various compounds. So that is the Gt. The Gt is equal to F into function of temperature. Total gift free energy of the solution is equal to function of temperature, pressure, number of moles of the various compounds, N1, N2, N3, so on, Ni, so on. Okay. Now for the little change in the temperature, little change in temperature, pressure, and moles of compounds. So then we can write this is dGt is equal to dou Gt by dou T at constant pressure, and number of moles. That is dt plus dou GT by dou P at constant, so this N is N, constant temperature, and N to dP plus dou GT by dou N1, constant temperature, constant pressure, N2, N2, N3, so on, Bn1 plus dou GT by dou N2, T, P, N1, N3, so on, Bn2 plus so on. You can write like that. We have already seen that. So that we have written same way. Okay. Now, so the term you can write. So that is dgt is equal to dou gt by dou t at constant pressure and dt plus dgt by dou p, constant temperature in N, dP plus we can write previous one as a summation I is equal to 1 to N dou GT by dou Ni, constant temperature, pressure, Nj is not equal to I, dNi. You can write like that. Okay. We already know chemical potential of a compound is equal to dou GT by dou Ni, constant temperature, pressure, J not equal to I. That we already know. So substitute that. So we will get the dGT is equal to dou GT by dou T comma N dt plus D, sorry, this is dou GT by dou P, constant temperature and P plus, so chemical potential this is, so mu, so we can write this one as a summation I is equal to 1 to N mu I dNi. Next one, we all know for the closed system, dZ is equal to, we have already seen in the second unit, the change in this energy for a closed system, that is VdP minus SdT. Okay, so but for a constant total change, that we can write a dGT is equal to Vt into dP minus St into dt. So at this now at partial derivation with respect to temperature, pressure, and number of moles, so we can get the expression is dGT is equal to Vt dP minus St dt. So with respect to the only temperature, dou GT by dou T at constant with only partial derivation, then constant pressure and number of moles is equal to, this term is 0, is equal to, we will get the minus Est. Okay, but only with respect to the pressure, dG by dou P at constant temperature and number of moles is equal to, so this will get the only Vt. Okay. So now you substitute them in the above expression. That expression is this one. So in that we already know that dou gt by dou t at constant pressure and n is equal to minus st. So here this is the minus st. So this is a Vt. So that we only finally we will get that dg is equal to minus st dt plus Vt dp plus summation I is equal to 1 to n mu I dni. So this is a total change in a Gibbs total change in Gibbs energy of the solution is equal to minus st dt plus Vt dp into summation I is equal to 1 to n mu I into dni. This is the fundamental relation for the change in free energy of solution. So what we have taken actually, we have taken in the previous determining the total molar property of the solution. In that we have taken at constant temperature and constant pressure. So then, but here what we have not initially we have not taken that constant temperature and constant pressure. But with respect to the temperature and pressure, how with that also how it is changing. Then we can write in other words, if the constant temperature and pressure, then we will get the only in the above expression that will be cancelled. dp term and dt term will be cancelled. Only dg, dg total at constant temperature and constant pressure will be the only summation I is equal to 1 to n mu I into dni. Okay. So integrate the both side. The integration of d g t at constant temperature and pressure is equal to integration of summation I is equal to 1 to n mu I into dni. Okay, so this is you get the g t at constant temperature and pressure is equal to summation I is equal to 1 to n mu I into ni. So this is the total change at constant temperature and constant pressure. What is the total molar property, total Gibbs free energy of the solution? Total Gibbs free energy of the solution is equal to the chemical potential of the each summation of the chemical potential of the each compound into number of moles. So that if it is a binary solution, this one we can write as G T total Gibbs free energy of the solution at constant temperature and pressure is equal to, for binary solution, mu1 n1 plus mu2 n2. So next one is the with how how this chemical potential is changing with respect to the temperature. If the temperature is changing in the solution, the temperature is changing, then with respect to the temperature, how the chemical potential is changing. So for that, we know already mu I is equal to chemical potential is equal to dou gt by dou ni at constant temperature pressure n j not equal to I. So that we know. So now derive with respect to the temperature. We know already mu I is equal to dou g T by dou ni at constant temperature pressure n j not equal to I. Derive this expression with respect to the temperature. So dou mu I by dou T at constant pressure and number of moles is equal to, so dou by dou T into dou gt by dou ni. We will this. Next one, this you can write dou mu I by dou T at a constant temperature and pressure is equal to dou square GT by dou T dou Ni will get. Okay, just to assume the expression. Next one. So we know already from the above chemical potential derivation, that is dou GT by dou T at with respect to the temperature at constant pressure and the number of moles minus St. Now derive this with respect to temperature again. Derive this with respect to the number of moles because number of moles. Then because in this expression, the above expression, dou T into dou Ni that is there. No, that's the reason. So with respect to the dou Ni, so dou Ni dou G T by dou T is equal to dou by dou Ni minus St. So this is dou square GT by dou T dou Ni is equal to minus dou St by dou Ni. Okay. So what is this expression? This expression is this. Okay. So now we can write whatever from here. We can write that from here. I'm just writing here. We can write here. So this is equal to dou mu I by dou T pressure and N. So dou mu I by dou T at constant pressure and N is equal to this one minus dou St by dou Ni. Now, so what expression we got? We got the expression this one. So this one we can write, because the expression we got dou mu I by dou T at constant pressure and N is equal to minus dou St total by dou Ni constant temperature, pressure, Nj not equal to I. We got this. And deriving the Ni means pressure and number of moles are there. So deriving this means get the constant temperature, constant pressure, Nj not equal to I. Okay. So from here, so this we can write dou mu I by dou T P comma N is equal to this one, write as a partial molar property of the compound. Means the with respect to the temperature, with changing the temperature in a solution, then how the chemical potential is changing with respect to the temperature, how the chemical potential is changing, that is equal to the partial entropy of that particular compound. Okay. Next one is the effect of pressure on chemical potential. Now, up to now we have seen what is the effect of temperature on chemical potential. The effect of temperature on chemical potential, that is equal to the partial entropy of the particular compound. Okay. Next one is effect of pressure on chemical potential. So we already know that same thing. So in this mu I is equal to dou T by dou Ni at constant temperature, pressure, Nj not equal to I. So that already we know. Now derive with respect to now same thing. We have to derive. Initially we have derived with the temperature, with the pressure. So now we know already what we know is equal to mu I is equal to dou gt by dou ni, constant temperature, pressure, n j not equal to I. Now derive this expression with respect to the dou by dou p. Mu I is equal to dou by dou p dou gt by dou ni. Constant temperature, pressure, n j not equal to I. So this is going to be there. Okay. So that we can write dou mu I by dou p at constant temperature, remaining other terms are is equal to dou square gt by dou p into dou ni. Okay. So same way you take the this term. What is that? What is that term? So dou gt by dou p at a constant temperature and number of moles, that is Vt. So now derive with the number of moles. So dou by dou ni, that is dou gt by dou p constant temperature and number of moles. This is equal to dou by dou ni into Vt. Okay, so now we can write dou square dgt by dou p into dou ni is equal to dou Vt by dou ni. Only ni changing, remaining are constant. That's the reason. Constant temperature. This is actually, sorry, this is Tn. No, Tn. This is now T and P and J not equal to I. J not equal to I. Because we are doing with respect to Ni, so remaining other things are constant. Constant temperature, constant pressure, Nj not equal to I. Okay, now we know already same thing. Equate them. Now we know this is equal to this is equal to, we know already, that is equal to d mu I by dou p. So okay, that is dou mu I by dou p dou mu I by dou p is equal to dou mu t by dou ni, constant temperature, pressure, and J not equal to I. Okay. So from there we can write. Dou mu I by dou p means the chemical potential. The chemical potential with respect to the pressure, that is equal to the partial molar volume of that particular compound. Partial molar volume of that particular compound. So in this way, how the chemical potential is influenced by the temperature. That is any particular. If you are interested, if you want to know what is the partial molar property, partial chemical potential of the particular compound with respect to temperature, that is equal to partial entropy of the particular compound, or with changing the pressure, chemical potential of the particular chemical potential of the solution with respect to the chemical potential of the particular compound in the solution with changing the pressure, that is equal to partial molar volume of that particular compound. So now up to now we discussed the what is a partial molar property expression, how many what is the reality in real situation, what is the meaning of that, how many methods we can determine. After that, we have seen the total molar property of the solution, total, and after that we have seen the chemical potential. Now chemical potential, we have seen how the chemical potential changing with respect to temperature, the change, how it is, then how with respect to the pressure, how it is changing. So that way we have seen up to now. So with this, we stop to this online lecture. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.